I'm going to assume you've already watched the introductory piece of solving problem number 5 from this old exam. Our main point that we want to do is we want to try to find this phasor value of voltage V sub 1 across load 1. We can't find that unless we had the impedance or if we had the current through that particular load. All we know is the complex power for load number 1. In order to obtain something useful that we can use to find voltage V1, we could find this current, I sub 2, the phasor form of that current. That's the same current as the current flowing through load 1. Once we know that current, we can use our complex power formula, which is VI star, and find the voltage that we want. But we're going to use this relationship for complex power a couple of times. We'll use it for load 2 first in order to find or solve for I sub 2 bar, and then we'll use I sub 2 to find V sub 1 in load number 1. Where we are going to start then is with load number 2. That's what we have in terms of enough information to work this problem. We're given that Q2 is a 80 vars, and since it's leading, we know that we have this minus sign. And our imaginary part of the complex power for S sub 2, S sub 2, remember, is P2 plus J Q2, or it's the apparent power magnitude at an angle of theta sub 2. We have now been given Q sub 2, and we know its sign because it's leading and it's vertically down. We can now find theta sub 2 from the power factor. The power factor in load 2 is just the cosine of theta sub 2. We were told the power factor, and we were also told that it was leading, and that gives us then this sign, or, well, we don't really need that sign in the power factor expression, so let me remove it, but we are told that it's a leading power factor. We'll need the sign when we start to solve for theta sub 2, which is the inverse cosine of this power factor 2, and here is where we can use the information about leading, and it's now a capacitive type load, and that's our minus sign. Or theta sub 2 is now minus the inverse cosine of 0.9, and that ends up being minus 25.84 degrees for load number 2. With that information, we can use our formula for the reactive power of load 2. Q2, remember, is the apparent power, which is the magnitude of our complex power times the sine of theta sub 2. We were given Q sub 2 in the problem statement. That was minus 80. We don't know the magnitude of S2, and the reason why we're trying to find that is so that we can actually find the complex power and use that together with V sub 2, the voltage dropped across that load, in order to solve for I sub 2. And we know, or we just computed, the angle theta sub 2. This now allows us to find the magnitude of our complex power for load 2. And finding that ratio, we end up seeing that load number 2 has an apparent power of 183.54 volt amperes. That's the magnitude. We can now use that to find P sub 2 to get the rectangular version, or I'm sorry, the rectangular component, the real part of our complex power, and that's S2 cosine of theta sub 2. We now have 183.54 times the cosine of 25.84. That could be a minus if we want, but cosine's an even function, meaning that won't play into the value for p sub 2, but now p sub 2, if we make that computation, and we were already really told what this was, that was 0.9, the cosine of our angle, and so we can just multiply 183 or take 90% of that and obtain for p sub 2 165.19 watts. Now we have our complex power S sub 2 in rectangular form. That's P, or the horizontal component, minus J80, there's our vertical component, or that's now 183.54 at an angle of minus 25.84 degrees. That we can use in our complex power expression to find the conjugate of our current flowing through that load, and then we can take the conjugate of that current to find the actual series current going through both of the loads, and that will then allow us to solve for V sub 1, which I can then use KVL to sum up V1 and V2 to find our source voltage V sub S. I sub 2 bar conjugate is then the ratio of S sub 2 over V sub 2, and S2, now that we're looking at a ratio, let's express S2 in polar form. We were already told what V sub 2 was in polar form and with RMS units, which allows us then to find I sub 2 in RMS. The 0 downstairs we will subtract as far as the angle from the angle upstairs, or we really aren't changing anything in terms of the angle. And our conjugate of the current flowing through load 2 is then in magnitude terms 183 divided by 5, or that's 36.708 at an angle of minus 25.84 degrees. Or we now can conjugate that to find I sub 2, the current flowing through load 2, which is 36.708 at an angle of 25.84 degrees. What we know is, since they're connected in series, that I sub 2 is the same as I sub 1, and we know we know I sub 2, and we can find our complex power S1, just that's given to us. It was 50 watts at 30 VARs, so we have our real part, 50, and it's now, we were given the sign, that was 30, plus 30, and so this is now our P1 plus JQ1 for the complex power of load number 1. It's probably going to be easier because we are going to be doing a ratio to find V1. Let's go ahead and find the complex power in polar form, or the apparent power at a particular angle. This is going to be a little bit larger than 50 because we have the square root of 50 squared plus 30 squared, which ends up being 58.310. Remember, our power triangle is now 50 here, complex power triangle, it's 30 here, and our complex power then for S1 has an apparent power of the length of that hypotenuse of that right triangle and the angle theta 1 right there. So we're really just finding the hypotenuse of that right triangle to find this polar form version of the complex power. It's now 58.31 at an angle that is the inverse tangent of the opposite side over the adjacent side, or the inverse tangent of 3/5, which gives us 58.31 at an angle of 31 degrees roughly. Let's just say 30.964 degrees for S1. Now we're in a position to use our complex power formula, which is V1 I1 star, or I1 conjugate. We know I1, so we know I1 star. Since I1 is I2 in this circuit, they're in series. This now allows us to solve for V1. V1 is just the complex power of that load, S1, divided by the conjugate of the current, I1 star, or we now have 51.310 at an angle of 30.964 degrees, all divided by the conjugate of our current flowing through that load, which I1 had a magnitude of 36.7, had an angle of 25, but we need the conjugate, so we now have a minus 25.84. We now simply take the ratio of those magnitudes, which is going to be a little bit less than 2. So we have 1.588 at an angle of 31 minus a minus 26, or that gives us then this 56.804 degrees. And it may be helpful to actually write that in rectangular form, because we're going to be doing the sum based on KVL. And if we take that then as 1.6 times the cosine of 57, we will end up with a real part of the voltage being 0.86944, and the imaginary part is going to be 1.6 times the sine of 57 degrees, or 1.3288. That's volts in RMS. Now from our KVL of the original circuit, we have minus V sub S plus V1 plus V2 is equal to 0, or V sub S, and that's the phasor form of V sub S, is just the sum of V1 and V2. V1 we just computed to be this value of 0.86944 plus J 1.3288. We need to add to that V sub 2, but V sub 2 was just 5 at 0 degrees, so it's now 5 plus J 0. We add up vectorially, or we add the real parts and the imaginary parts to obtain V sub S is now 5.86944 plus J 1.3288. That's now our RMS voltage for the voltage source, or if we wanted to, we could express that in polar form, find the magnitude of that complex number, which is the real part squared plus the imaginary part squared, square rooted, or this now becomes 6.018 at an angle of an inverse tangent of opposite over adjacent, which if you do that, you end up with 12.76 degrees volts RMS, and that then is our voltage across the two loads.